Hello, my name is Al Season, and I'm the RTCA Vice President of Aviation Technology and Standards. Over the past several months, RTCA has been bringing you online webinars called Aviation Technology Connect. After our symposium had to be canceled in June, we wanted to find another way to keep you posted on the trends we see in our industry. The webinars are high-level discussions on topics like aviation safety, counter UAS measures, commercial space, and ICAO perspectives. Those webinars have been very successful. Thank you. Today, we start an additional second series of webinars. This series will highlight the work of various RTCA committees at a deeper level. In so doing, we hope to reinforce for you the value of RTCA committees and the documents they produce. Today's webinar highlights the work of Special Committee 239, Low Range Radar Altimeter. The committee was formed in December 2019 and tasked with updating the current minimum operational performance standard for low-range radar altimeters, DO 155. The committee is focused on protecting future radar altimeters from existing and future in-band and out-of-band interference. Following the committee's presentation on their work, there will be an interactive Q&A session. We encourage you to submit your questions via the Q&A panel on your screen. Speaking today will be the leadership team of Jean-Luc Robin, Seth Frick, and Dr. Sai Kalyanaraman, as well as Terry McVenis, President of RTCA, who will moderate the Q&A session. You can find videos of our past monthly Aviation Technology Connect webinars on the RTCA YouTube channel. This webinar will be posted to that channel within a few days also. Today's webinar is brought to you by the generous sponsorship of Collins Aerospace, NBAA, American Airlines, and Garmin. We are grateful for their support. Please remember to look for the virtual handouts from today's webinar by clicking on the Documents icon. Those handouts include a link to RTCA's recently published white paper on assessment of C-band mobile telecommunications interference impact on low-range radar altimeter operations, the slides from today's presentation, and handouts from our sponsors at Collins Aerospace and Garmin. And now, I'll turn the webinar over to the SC239 leadership team. Thank you for tuning in.
Hello, everyone, and thanks to RTCA for organizing this webinar. Today we'll be having a presentation and some discussion on the interference risk to radar altimeters from planned 5G telecommunication systems.
Hello, hello everyone, I'm Jean-Luc Robin, and I'm the radio navigation expert at Airbus, and I'm serving as co-chair of SC239 along with Seth.
And this is Seth Frick. I'm a radar systems engineer at Honeywell, and as Jean-Luc mentioned, one of the Special Committee 239 co-chairs.
Good morning, good afternoon, everyone. I'm Sai Kalyanaraman. I'm a technical fellow at Collins Aerospace, and I support SC239 as secretary.
Okay, so to understand the issue of interference to radar altimeters, first and foremost, we need to have a good understanding of radar altimeters, how they work, and how they're used in civil aviation. So fundamentally, radar altimeters are exactly what they sound like. It is a full radar system. It's a downward-looking radar system with the antennas installed on the underside of an aircraft, which transmits an RF signal towards targets. In this case, the targets are the terrain or any obstacles that can be protruding above the terrain. And then the system receives a reflection of those signals off of those targets back at the receiver and measures the time delay to determine range to those targets. And in the case of an altimeter, the range to the terrain is going to be equal to the aircraft's altitude above ground level. And it's very critical to note that radar altimeters are actually the only sensor on an aircraft that can make that direct measurement of AGL altitude. So typically when you talk about altitude or an altimeter measurement on an aircraft, you're referring to something like a calibrated pressure altitude from a barometric altimeter or an air data system, or in some cases GNSS altitude. And in those instances, the altitude measurement is going to be referenced to some sort of absolute datum or reference point, for example, sea level or an ellipsoid height. So if the terrain that the aircraft is flying over is not equal in elevation to that absolute datum or reference point, then that information of absolute altitude doesn't provide any indication of the aircraft's clearance height or safe clearance height above the terrain or any obstacles. So the radar altimeter is very critical in its ability to provide that measurement directly, unlike any other altitude sources on the aircraft. So with that direct measurement of AGL altitude, the altimeter serves its most critical function, which is providing situational awareness of the terrain to the flight systems and pilots to prevent any sort of controlled flight into terrain or CFIT type of occurrence. And CFIT accidents are actually what really led to widespread use of radar altimeters in civil aviation beginning in the 1970s, including some high-profile accidents such as TWA Flight 514 in 1974, in which there were actually no survivors of that particular crash. 92 people on board, including passengers and the flight crew, all perished in that case due to a CFIT accident. So today, radar altimeters are ubiquitous across a wide range of civil aircraft, including not just commercial transport airplanes, but also business and general aviation airplanes, as well as helicopters. So radar altimeters operate in a global protected aeronautical spectrum allocation, in this case from 4.2 to 4.4 gigahertz. And within that band, they will typically employ either pulse radar technology, which is generally what most people think of when thinking of a radar system, emitting short bursts of RF energy and then waiting for that pulse to be received back and measuring the time delay. Or actually what's more common in the radar altimeters used today in civil aviation is what's called frequency modulated continuous wave, or FMCW technology. So in this case, the radar altimeter, instead of emitting pulses, will actually be transmitting continuously with 100% duty cycle. And the particular waveform that's used will include a series of linear frequency sweeps, or chirps, where the frequency is changed linearly over time, as shown in the figure on the bottom left here. So in this case, when the altimeter receives a signal, which is essentially a delayed and attenuated copy of the transmitted signal, we can just look at the frequency difference between those waveforms, and then knowing the slope of the linear FM sweeps, we can also determine the time delay, which will be directly proportional to that frequency difference. So this is usually done with what we call a homodyne or zero IF architecture in the RF system, in which case we actually take that transmitted signal and couple it off to feed the local oscillator of a mixer in the radar altimeter receiver. And then the output of that mixer after low pass filtering is going to be a signal at the difference frequency between the transmitted and received signals. And then that again is that frequency is going to be directly proportional to the time delay and thus the altitude. So with some amount of signal processing to determine the frequency of that signal, we can make an altitude measurement. And as mentioned before, radar altimeter usage is pretty ubiquitous these days in civil aviation. And the usage of altimeters has gone far beyond just providing that AGL altitude indication to the pilots on a display or something like that. In particular, on commercial transport airplanes and some of the higher end business and general aviation aircraft, the radar altimeter output is fed into a wide range of systems, safety and navigation systems on board the aircraft. So you have not only things like the Terrain Awareness and Warning System, or TAWS. The altimeter is also used to activate or inhibit functions in other sensors, such as wind shear surveillance in the weather radar. It's also used as a key input to TCAS. And it's also these days, very tightly integrated into the flight control systems, including functions such as automatic landing and auto throttle during approach and landing procedures. So all of these functions are, of course, very safety critical, and the radar altimeter plays a very key role in that. And then finally, the last thing that's important to understand regarding radar altimeters and how they're designed and operated is the actual requirements that are used to define their performance. So generally in civil aviation, radar altimeters will be certified at the equipment level through what's called the technical standard order process, which is a pretty rigorous certification process that requires extensive validation and testing of the radar altimeter design against some standardized set of performance requirements. And those requirements may be defined in the TSO itself directly, or by reference to some outside industry standards, such as a minimum performance specification or minimum operational performance standard, or MOPS, as we call it. And those types of documents would be generated by typically an independent standards organization, groups such as RTCA or EuroK in Europe. And then those two groups, of course, often work very closely together in collaboration to develop those types of standards. Initially, the first set of standardized radar altimeter requirements for civil aviation were provided in TSO C87, which was released all the way back in 1966. And that document did include the requirements directly within it. The requirements in TSO C87 were ultimately essentially incorporated into an RTCA MOPS DO-155, which was released in 1974. And then that TSO C87 set of requirements stayed in effect all the way until 2012, when it was eventually superseded by TSO C87A. And C87A now references performance requirements in a EuroK MPS ED30, which was released in 1980. So even though the TSO was updated, the performance requirements themselves are still quite old in this case. So regardless of which set of requirements you're talking about, all of these standards have not had any real specific requirements regarding interference susceptibility or receiver masks or anything like that, other than just very general requirements regarding interoperability in multiplex installations on the same aircraft. So there's nothing really governing the out-of-band interference environment. And that may sound a little strange, but when you think that the last update to any of these requirements was 1980, what did the RF spectrum environment really look like way back then? Cell phones certainly didn't exist. The threat space was very different, and RF interference was not really considered to be the same type of threat at the time that it is today. And so with that, I'll hand it off to Jean-Luc to discuss in a little more detail what that RF spectrum environment looks like.
So thank you very much, Seth, for this comprehensive introduction. And so now what we will see before looking at what is going to be the future of RF environment, we will see the current radio frequency environment today. So basically, the spectrum surrounding radar altimeters is dominated by fixed services and fixed satellite services. And so fixed services may have high radiated power, but as they are sparsely distributed, and they use highly directional antenna, so with very short and small beam width, the radio altimeter are not affected with these services today. And the second thing is the fixed service satellite services. So the signals are coming from space and are largely attenuated by more than 30,000 kilometers away, so that we have very low interference at radio altimeter. So that radio altimeter are not affected today by fixed satellite services. We also have above the 4.4 gigahertz and aeronautical mobile telemetry used by federal organization today, and they are generally insulated to specific test ranges. So we have a table at the right with different regions. So currently, high power interference so basically we have a quiet knife bore today, and we can have high power emission also coming from ground-based surveillance radar, but they are far from the band, and they are sparsely distributed also, and with very narrow beam width. So it's transparent to our radio altimeter. So, however, we have airworthiness standard, but regarding the high intensity radiated fields, so we test a continuous wave and pulse high power interference signal. However, we have an exclusion band. This exclusion band is allowed at plus or minus 10% around the band. So it means that this band that is not tested today, and that is not considered today in terms of interference, spans from 3.78 and 4.84 gigahertz. Therefore, today Earth requirements are not enough to protect our radio altimeter, and regarding the next ongoing modern communication that is coming closer and closer to the radio altimeter band. So now, what is the evolution of the interference environment that we have to cope with? So in the mid-band, so radio altimeter lies in a very spectrum sweet spot, the mid-band. And this spot is very, very attractive because first here you have very interesting throughput capability for data rate, and at the same time you have very, very interesting propagation signal properties, so that everyone wants this band today, and especially a 5G mobile wireless application. So it's why United States and the FCC has made the mid-band spectrum a priority for 5G technology deployment. And this include band from 3.45 and to the 3.55 gigahertz, but also 3.7 to 3.98 gigahertz, which is close to our band. And this mid-band spectrum is extremely valuable. As you can see, the cost of the megahertz is very high. So this is the landscape of the worldwide 5G deployment, and as you can see, the radio altimeter is at the middle of 5G deployment. And especially you can see the USA, but also the Canada, the Australia, and the Japan, Europe, and UK. So China. So a lot of all country is establishing on this band. So with some ground band sometimes not, and with different level of power. So this has to be taken into account in the analysis. So now Sai is going to present you the study of the RTCA report that we have performed.
Thank you very much, Jean-Luc. Given the excellent backdrop that Seth and Jean-Luc set up in terms of what a radar altimeter does and some of the evolution in the spectral environment, we can get into the details of what was performed within the auspices of RTCA. And while I'm getting into that, I'd like to provide a quick overview of the background of how we got here. Back in 2018, FCC had announced its plans to establish a new spectrum allocation for 5G and LTE systems in the band adjacent and below to radar altimeters. They were looking at utilizing the band between 3.7 and 4.2 gigahertz for that. Once this intent was announced, given that in the radar altimeter community, we understand the pushes and pulls of what spectrum compatibility is, there was some additional activity that was pursued within the auspices of AVSI, which stands for Aerospace Vehicle Systems Institute out of Texas A&M University. And we conducted initial testing and analysis to evaluate what the high-level risks would be for radar altimeter systems that are operating in the band between 4.2 and 4.4 from 5G transmissions in the near band in the 3.7 and 3.98 gigahertz to begin with. We did understand that there was a plan to amortize the 3.7 to 3.98 gigahertz, and we focused on that as the scope of the activity that was initially conducted within the AVSI forum. AVSI and its membership, including industry and folks from the FAA, also put together a high-level report, and AVSI and its membership met with the FCC to sensitize them of the potential issues that may come to play when this band is utilized by 5G and LTE systems. And pursuant to those discussions with the FCC did acknowledge in its March 2020 report and order that further study was necessary to address coexistence between radar altimeters and 5G systems. But at this point in time, they had not shared any information on possible operating limitations to account for the safety and the operations of radar altimeter systems. So that essentially set forth the need for us to go ahead and do a deep dive on what these issues are and what could happen in the future if 5G systems were to operate right next to the band where radar altimeters operate in the 3.7 to 3.98 gigahertz. So given that backdrop, within RTCA in April of 2020, we concluded that we'll have to start working on the evaluation of this interference impacts, and RTCA SC239 established a special task force. It is to note that the SC239 was a relatively nascent working group that was set forth initially to look into evaluating what is needed for a next generation radar MOPS. But given the alacrity with which we have to address this issue, RTCA went ahead and established a special task force to evaluate the impacts to radar altimeter from 5G systems in the adjacent band. And there was a fair amount of work that was performed within the auspices of SC239. It was a multi-stakeholder group, and it was open for public participation, i.e. anybody from industry can look to register and participate in the activities within SC239, and it was open to membership as well as people who were not members of RTCA. And at the end of the activity in October 2020, SC239 released a public report and provided that report to the FCC, and there was an adjoining ex parte presentation that was made to the FCC, which can be found on the FCC website as well. So having set that background, let's talk about what the crux of the issue is. As you see on the left, on the top left, you have a pictorial that depicts the current situation spectrum-wise in the band near the radar altimeters. Radar altimeters, as mentioned earlier, occupy the 4.2 to 4.4 gigahertz. And as you can see in that pictorial, you have between 3.7 and 4.2 gigahertz, you have FS, which is a fixed satellite and fixed satellite service satellite emission spectrum that is right below the radar altimeter system. Now, with the FCC RNO, whenever it goes into effect and 5G LTE systems start rolling out their base stations and start transmitting that band, you will expect to see a high-powered system in the band below radar altimeters between 3.7 and 3.98 gigahertz. In order to facilitate these high-powered systems in the band right next to radar altimeters, FCC has incentivized FSS providers to move out of that band and move into the band between 4 and 4.2 gigahertz. So you would still have transmissions in the band between 4 and 4.2 gigahertz that would typically be fixed satellite systems. And you would see that there is additional emissions, which are spurious emissions, out-of-band emissions that would fall from the base station transmissions that happen at 3.7 to 3.98 gigahertz into the band between 3.98 and all the way up and above the 4.4 gigahertz. Now, it is to note, as Seth mentioned earlier, and as Jean-Luc alluded to, that there isn't a specific out-of-band rejection requirement for TSO radar altimeters. And if you dial the clock back and look at what was in that band when these standards were set, we did not have high-powered base station systems. In fact, when these standards were set, cellular telephones did not exist. So that being said, when you're looking at the existing situation in the top part of the slide, you see that you have a radar altimeter certified safety of life system that's operating in the 4.0 to 4.4 gigahertz band. And what's in the adjacent band is a low power spectral flux density system. And we're looking to essentially rezone the neighborhood and change the characteristics of the power spectral flux density in the neighborhood from a low power system to a high power system. And the concern that SC239 had put forth is that these high powered systems could typically cause a fair amount of receiver blocking for the receive part of the radar altimeter systems. And we'll get into the details in the next slides. So this is a high-level overview of the study approach that was espoused by SC239. SC239 looked at what information was available in order to perform the evaluation of the potential impacts from 5G and LTE systems to radar altimeters. On the top left, you can see that we leverage the existing industry standards, and these are aviation industry standards and telecom industry standards and ITU standards. We took additional input and information on the specific 5G technical characteristics that were provided by CTIA and telecom participants of what was called the Technical Working Group 3, which was set forth in order to address compatibility concerns between aviation systems and 5G systems. That was a separate technical working group, and we obtained input from that working group into the multi-stakeholder forum that has been set forth under RTCA SC239 to perform the specific evaluation of impacts to 5G from 5G systems to radar altimeters. And on the bottom left, you see that we took input on radar altimeter technical characteristics that were provided by the aviation industry that typically designs, manufactures, and fields these radar altimeters. So all these inputs were fed into two categories of items. We took inputs from the 5G technical characteristics and the radar altimeter systems and performed empirical evaluation of thresholds. And these are the thresholds up till which you can operate these radar altimeters in the presence of 5G interference. And this was performed across a suite of different radar altimeters. We evaluated up to 9 radar altimeters from different manufacturers, and these 9 different model types were subject to interference testing based on the 5G technical characteristics that were provided. And we came up with empirical interference thresholds that we would need to pay heed to in order to operate these TSO radar altimeters in a safe manner. So that's what you see on the bottom of the chart in the green box. In the gray box above, we leverage the input from the 5G systems and input from industry standards to evaluate how much of power you would see from a given base station or a given handset in specific configurations with different antennas at different points in space. So essentially, you have 2 inputs that are coming into play here. One is the actual intrinsic evaluation of how much interference that these radar altimeters can tolerate at different frequency offsets from the radar altimeter band. And this is interference that would emanate in the 3.7 to 3.98 gigahertz. We did testing taking 100 megahertz chunks of bandwidth that the base stations can use for their 5G transmissions. And we essentially tested all the way across 3.7 to 3.98 gigahertz. So that's the intrinsic radar altimeter empirical interference tolerance threshold, and then you take that threshold and you bounce that against how much power you would potentially see from these base stations for the given EIRP that these base stations are authorized up to, and at different look angles from the base stations based upon the antenna patterns, and at different altitudes and distances from the base stations. So essentially, we have two parts to this. One is an analytical part and one is an actual testing part. And the way we've set up this activity is such that once we have this data that we have collected now through the auspices of the SD239 activity that's been supported by the AVSI testing activity, we are able to now bounce it against the analysis part that you see on the top part of the chart in the gray box. So as we move forward, if industry were to go ahead and evaluate what the impact to radars that are TSO today would be from a different base station layout or a different level of power from these base stations, we have all the information that we need based on the empirical testing that was done, and you'll have to bounce it against the simulation and analysis that you would get from an updated set of assumptions that would be reflective of what we have in this gray box. Now, the output of that is to identify the scenarios where you would expect, based on the existing assumptions of base stations and layouts, where you would expect impacts to radar altimeter systems, and we'll get in that in the next couple of slides. And as indicated in one of the earlier slides, the way we've been analyzing the impacts to radar altimeter systems is based upon the ICAO guidelines. We were looking to analyze the worst case impacts under ICAO guidelines of safety margins. Now, as you can see in this slide, this talks about what's called of usage category 1. When we did this evaluation of impacts to radar altimeters, we looked at what are the different CONOPS under which we'll see impacts to radar altimeters, and we essentially broke down the trade space of radar altimeters into 3 categories. We called them usage categories 1 through 3, and usage category 1 reflects the radar altimeters that are utilized on commercial air transport aircraft and on commercial large big iron cargo transport aircraft. And usage categories 2 and 3 reflect the relatively smaller business and regional aircraft and children aviation in the category 2, and usage category 3 typically reflects the helicopter platforms and other rotorcraft platforms. Now, looking at the specific details of impact to usage category 1, as you can see on the plots on the right side top, you see as indicated that there are red dots in a specific set of regions in this chart. And based upon the assumptions on the base stations, in this case, for the usage category 1, if you take a urban base station assumption, which has its associated EIRP levels, and you take a 16 by 16 active antenna array system with a -30-degree vertical scan, and you have a straight in and level approach case where you have your aircraft straight and level, and there's 0-degree aircraft pitch or roll. So essentially you're coming in for an approach. And at that point, you see that based on the assumptions of these 5G systems, for a distance of anywhere between 0 to 0.4 miles between the base station and the aircraft, all the way up to altitude of about 4,000 feet, you see that the interference levels from these base stations under the current base station EIRP and antenna pattern assumptions that were afforded us by the telecom industry, you would have interference at the input of the radar altimeter at the aircraft that is in excess of the safe levels. And I'll get into the details of what that safe level means in the next chart, but this is to note that based upon a specific antenna pattern assumption and specific scan angles, you would anticipate a high level of interference that is in excess of what the safe limit is for radar altimeter operation. Now, the trade space of the different base station layouts that impact the usage category 1 is limited, but from a cost function perspective, even though the trade space is limited, the impact is severe, because when you're looking at usage category 1 aircraft, if you have a unreliable radar altimeter signal return that is being interpreted by the radar altimeter, and that can cause multiple different things that include loss of function, and this is loss of critical function. It could potentially cause hazardously misleading information, and that is not desirable because the output from the radar altimeter sensor is coupled into a variety of critical aircraft systems that include flight controls, terrain avoidance, cockpit displays, and autopilot. And given that this is a extremely critical sensor for the purposes of performing your approach, landing all the way down to touchdown, you could potentially have catastrophic impacts, and that can essentially lead to multiple fatalities on the ground. So from that perspective, it is extremely crucial to take a strong look at the impacts from these 5G base stations to radar altimeter systems for these usage category 1 aircraft and the other usage categories as well. It is to note that the impacts are relatively lesser for usage category 1. We don't anticipate any specific impacts from spurious emissions of these 5G systems for usage category 1 aircraft at this time, based upon the assumptions that we have, but we do expect impacts from the adjacent band to the radar altimeter system, which is the 3.7 to 3.98 gigahertz. So if you have transmissions of 5G base stations from the 3.7 to 3.98 gigahertz in the adjacent band, these fundamental transmissions that could cause blocking of the receive system on the radar can potentially cause a situation where you could have a catastrophic impact to the ground under these base station assumptions. So that being said, let's talk about what we see for the other two categories in the next couple of slides. So having spoke about category 1, let's look at usage categories 2 and 3. And as you see at the top of the screen on the left, usage categories 2 reflect the business aviation and the general aviation of the regional transport planes, and category 3 is typically the transport and general aviation helicopters. We've stated that this would typically be helicopters, but as we move forward, you could expect to see a variety of unmanned aircraft as well, using radar altimeters for their operations. So it's essentially rotorcraft and possibly unmanned aircraft as well that will be using radar altimeters here in the future. Now, unlike the limited cases that we looked at from the perspective of addressing the possible concerns of interference from 5G systems or radar, there is a huge number of cases that are involved when you're looking at usage categories 2 and 3. And that is an artifact of what the CONOPS of these categories are, in addition to the exposure of some of these radars to adjacent band interference systems. When it comes to CONOPS, you can see that if you potentially have a helicopter medevac system that is looking to go ahead and land atop the roof of a hospital, or it's going to have to land in certain zones to go ahead, pick up patients who are critically injured and they have to be transported back to the hospital, they are looking to land the helicopter pretty much where they can, and these could be in urban areas, and you can essentially have a flight path that cuts right through the main beam of these 5G/LTE base stations. So given that a priori, I'd like to get into the details of what the slide over here shows. And if you can focus on the pictorial in the slide, you see that there is a solid black line at the bottom around the minus 78 dBm per megahertz range. Now that solid black line is what's called a interference tolerance mask. That essentially says that as a function of altitude, you could see that there is a level of power spectral density that should not be exceeded by the power transmissions as seen at the input of the radar altimeter at the aircraft. And that is a level that is seen in black here that would ensure that you would make sure that you don't have a safety impact to the radar. Now, the black line is now supported by a shaded area in pink in there, and that is to show the safety margin from a ICAO standard perspective. And as seen in the ICAO 9718 handbook, we typically have a 6 dB safety margin for safety of life systems. So although the interference tolerance mask is the stress case mask that shows that level at which you can reach and have interference up to the point where you don't have a safety issue on the radar, in order to ensure that you're accounting for variations in path loss, you're accounting for multipath, you're accounting for the safety criticality at whatever levels you have to address on the aircraft. So you may have some systems that are critical down to a 1E-9 per hour, some systems that are critical at 1E-5 per hour. We have a safety margin for aviation systems So essentially, the ask from aviation is any transmission that can show up at the input of these radar altimeters on the aircraft for the categories 2 and 3, and especially in this figure for category 2, should be at or below the bottom end of that pink zone that you see on the slide. Now, that's the reference point from a safe operation perspective. What you see right above in that plot are curves as a function of different assumptions that were made and the reflection of the simulation results that go along with those assumptions. So let's pick one of those curves over here. We can pick the one in dotted blue that essentially talks about expected 5G interference levels. That essentially reflects a rural 16 by 16 active antenna system. So with the 65 dBm EIRP that you have for the existing base station 5G LTE assumptions, if that base station were to use a 16 by 16 active antenna system and it uses the power levels for the rural rollout versus the urban rollout, that is the curve that depicts the amount of power that you'll be seen at the radar altimeter receive port on the aircraft as a function of aircraft altitude. And then you have a slew of other curves that reflect the 8x8 active antenna system for the urban zones, and they have the suburban 8x8 active antenna system. They have the 16 by 16 antenna systems. You have sectoral systems. So we have a variety of different antenna assumptions that we vetted with the CTIA stakeholders. And as you can see here, any and all of these assumptions in conjunction with the fundamental EIRP that's afforded in the FCC RNO will be a threat to platform categories 2 and 3. So from that perspective, we have a substantial concern of receiver blocking from the adjacent band transmissions. And it is to be noted that in this case, there is a concern with 5G spurious emissions as well. It is not just the underlying receiver blocking impact on the radar from fundamental transmissions in the adjacent band. We also see that there is a substantial concern from emissions from these 5G systems in the adjacent band that could fall right into the middle of the radar altimeter band, which is the 4.2 to 4.4 gigahertz band. Now, when it comes to a situation where you're dealing with the emissions from out of band that falls into your main band, there isn't a whole lot the radar altimeter systems can do. Even if you have any additional filtering in future radar altimeter designs, that is not going to help because this is energy that falls right in the middle of the radar altimeter band that is being used to process the returns from the radar altimeter pings. And with that, we can go to the next slide. We're looking into discussing the continuation of these efforts and where we're going from here, and at which point I'd like to turn it over to Jean-Luc Robin.
Okay, thank you very much, Sai, and thank you very much, Seth, for this thorough presentation. Now we know why radio altimeter are so much important for the aircraft. We know why we have to struggle with new radio frequency environment, and what is the challenge that is ahead of us. So what is the next step now? So we have created RTCA SC239 jointly with EuroCAE Working Group 119 in order to define and to develop a new MOPS in order to specify the interference tolerance requirements in order to have resilient radio altimeter in the future. But while this MOPS will be revising, the current fielded radio altimeter will still be exposed to 5G interference. So this is the problem we have to cope with today. So what will the FCC do? Actually, aviation industry has proposed some mitigation to be implemented for 5G in 5G deployment, but the outcome is uncertain, and we are waiting for FCC answer. What will the FCC do? So depending on the FCC answer, so we don't know today. It's unclear what FAA will do if we will have some mitigation means, or if we will not have mitigation means. So this is what conclude this presentation, and I thank you everyone for your attention, and we'll give the stage back to Thierry.
Well, thank you, Jean-Luc. Great presentation. My name is Terry McManus. I am the President and CEO of RTCA. I'd like to first add my welcome to everyone for joining us today. Also want to take a moment to thank the sponsors for today's webinar, Collins Aerospace, NBAA, American Airlines, and Garmin. Putting on these webinars just wouldn't be possible without their support, so we thank them. I do want to remind everyone that on the handout sections of this platform, there are a number of things that you can download, including the slides that were used in the presentation. And there's also a link to a great video rendition of our report that an Emirates Airbus A380 captain has put together. Again, you can access those documents just by clicking in that handout section. So with that, I'd like to invite the presenters back on to start a little bit of question and answer period. So Jean-Luc, Seth, Sai, welcome you back. Thank you again, guys, for just a wonderful presentation, a lot of good work here. Somebody told me a long time ago that without facts and data, you're just another person with an opinion. So can you guys kind of run me through and the audience through a little bit about the data that was used, who provided that data, and a little bit of background on it?
Yeah, I think I can kick us off a little bit there, Terry, and Sai and Jean-Luc may have a little bit to add. But as we mentioned in the presentation, the testing efforts that were conducted in support of the SC239 study were carried out by AVSI, the Aerospace Vehicle Systems Institute at Texas A&M. They were a great help in that effort, and they were, a natural choice given that they had already conducted some previous radar altimeter testing for other interference cases. So they already had several of the altimeter models available. They already had a test bench that could be used with just a few minor tweaks. And the data that was ultimately provided from AVSI to SC239 consisted of data sets that took all of the measured tolerance thresholds across a given usage category. So I believe there were a total of 9 altimeter models that were tested. 5 of those were applicable to usage category 1 only, and the other 4 were applicable to both usage categories 2 and 3. So for each of the 3 usage categories, AVSI basically merged all of the test data into a single combined tolerance threshold, which represented the worst case performance of any of the altimeters in that usage category. And that served the needs of the SC239 study very well, because the way we scoped our study was to identify if there were any interference risks to currently fielded TSO authorized radar altimeters. We did not consider it within our scope to specifically identify which particular models may be susceptible to interference, but we instead wanted to focus on the different aircraft platform types and see if there was any risk as a starting point. So that was kind of the approach that was taken. It made it very easy in that regard for AVSI to share that data with RTCA for the purposes of our study. And from a technical standpoint, that was certainly sufficient for our needs.
Yeah, just to add to that, Terry, there was additional data that industry had collected on representative antennas as well that was used as part of the modeling and simulation effort. And this was used in conjunction with what information that we have today in ITR M 2059 to provide a more representative value of antenna selectivity across the band that would be in turn used for the modeling and simulation to evaluate the overall power that would be seen at the radar altimeter.
Did some of that data come from the telecommunications industry itself?
Yeah, absolutely. It's what I would like to add also that the data are also coming from 5G telecommunication industry, and mainly T-Mobile, AT&T, and Verizon, that provide us with a reasonable assumption of what is typical today as a 5G signal. So we also use this as an input.
Great. The original order that was published by the FCC stated that 220 megahertz of separation from the radar altimeter operations were going to be sufficient to protect aeronautical services in that 4.2 to 4.4 gigahertz band. Why does this RTCA report show that that wasn't correct?
Maybe
So
I can start a little bit, or maybe I can start to say something very quick. So the 200 megahertz guard band is about the spurious unwanted emission, but we discovered that we have also a blocking radio frequency phenomenon at the input of our receiver. So that the fundamental power outside the band is so high that the receiver front-end module are saturated.
Yeah, just to add to what Jean-Luc mentioned, when the FCC RNO was penned, there wasn't detailed empirical receiver testing tolerant masks available. So when we looked at the information, the FCC RNO, in conjunction with other submittals that were made to the FCC by other telecom stakeholders, it was evident that a detailed evaluation of the TSO radar sensitivity has not been done for interference that would emanate in the 3.7 to 3.98 gigahertz band. So when AVSI and its stakeholders provided the initial set of results to the FCC, it was clear that additional work needed to be done to resolve this concern. And in that context, within RTCA, we took upon this effort to go ahead and do a deep dive and test these radar altimeter models that are TSO'd in an exhaustive fashion. And whilst we were doing that, we got more information on the parameters of the telecom rollout that would happen in the future. And we realized that the spurious emissions, similar to what Jean-Luc has mentioned, were substantially higher. And based on the RNO, if those spurious emissions were to be found in the environment when we are operating radar altimeters, we would expect to see a substantial amount of power show up in the radar band. So whilst we started looking at this from the perspective of addressing possible radar receiver blocking, we also saw that there's substantial spurious emissions that would impact platform categories 2 and 3. And that was a completely new item that we discovered pursuant to performing this deep dive activity. So in the context of where we were at, Terry, when the FCC RNO was penned, and having obtained additional data from telecom stakeholders and evaluating the intrinsic radar altimeter receive system performance from an empirical fashion, it is absolutely true that we needed to have this RTCA and AVSI activity take place to provide clarity on what the technical impacts are. Over.
Right, and just to add a little bit more on that. So the FCC order, when they said that they think 220 megahertz should be enough guard band, there wasn't really any supporting data or analysis provided by the FCC directly. So there was no opportunity either for the aviation industry to make an assessment of that claim and ensure that the correct assumptions and data were being used as inputs. So that was a kind of a concerning thing that we saw there, especially as we conducted the study within SC239 and found a very different conclusion. And it's, 220 megahertz certainly sounds like a lot of guard band. In many other contexts, it certainly is. But the radar altimeters are inherently very wideband systems. They typically will utilize nearly 200 megahertz of bandwidth themselves in the receiver. So speaking in terms, relative to the actual utilized bandwidth of the radar system, it's not as much guard band as it would sound like. And in particular, most of the radar altimeters that are currently fielded and have TSO authorizations were designed, many years or decades ago without any specific requirements for tolerating out-of-band interference with any amount of guard band. So it's our position with the FCC has always been that we recognize that the spectrum environment is changing. We're working to update our requirements to reflect that. But the fact of the matter is that the data that we've seen in the radar altimeter testing is what it is, and that indicates there is going to be a potential risk of harmful interference, and that needs to be addressed because 5G rollout is going to happen at a quicker rate than the aviation industry can respond with new requirements and developing and certifying new hardware.
The approach that was taken in the analysis utilized a worst case scenario, both for analyzing the radio frequency interference as well as the worst case landing scenarios. Some might say that this is being overly conservative and doesn't depict a real world situation. Why was this approach taken in the analysis?
I can give some first element of answer. Terry, this is a very good question. Actually, we took two margin, one to account for the dispersion of hardware component, and the second one for safety. So for the first one, regarding the dispersion of hardware component, we have taken this margin to account to the fact that we only test one serial number unit. So we tested 9 radio altimeter, but we only account each time for one serial number unit. And so we have also to account with the temperature, because in laboratory it's 25 degrees, so we have to account for that. And deeper measurements that are ongoing today on several serial number reveals today that those 6 dB margin are likely to be probably too much optimistic. So due to mainly roll-off and cutting frequency. And for the safety margin, so the safety margin, ICAO safety margin, is needed to account for unknown, but it's largely justified because, for instance, we did not account for base station located on the top of a mountain or on the top of a building. We only account for one base station mast. We only tested one modulation, one 5G modulation with one separate subcarrier. And we were also in a perfect radio frequency environment in laboratory. And we also, for instance, use active antenna model, the 2101, that is probably also optimistic.
Seth, I think it was in your introductory parts about radar altimeters. You talked about the two different types of radar altimeters. Are there any expectation that those pulse mode radar altimeters in general are less or more susceptible to this interference phenomena?
Sure. So as I did mention in that intro, at least in civil aviation, pulsed altimeters are far less common these days. They used to be a little more common than they are now. Although there's also non-civil aviation use cases with military aircraft, and in that arena, pulsed altimeters are actually far more common than FMCW altimeters. So there still are quite a few military altimeters, or pulsed altimeters rather, flying today. And the SC239 report didn't specifically consider military altimeters due to a variety of reasons, and the time constraints that we had to try to get the report out. There's not much from a technical perspective that would indicate one of the technologies is going to be inherently more susceptible than the other. Of the 9 radar altimeter models that were tested by AVSI, I believe 1 was pulsed, and all of the remaining 8 were FMCW. So there's not a whole lot that can be gleaned from that test data. But one thing I will say is that the topology of a pulsed radar architecture does generally make it a little easier to mitigate any out-of-band interference with either a retrofit or a redesign to include a more aggressive bandpass filter roll-off response in the receiver front end. From a technical standpoint, that may not be a feasible solution for all FMCW radar altimeter designs, because in that case, inserting such a filter may impart some imperfections within the radar altimeter bandwidth, such as group delay variation, which can have some other impacts to both sensitivity and accuracy performance. So generally, while there may not necessarily be anything inherent in the design that makes one more susceptible than the other, I think at least for the out-of-band blocking case, it may be something that's easier to mitigate with a pulsed altimeter design than with FMCW.
Got a question here, kind of more from an operational standpoint. If the aircraft is moving at an approach speed, you're going to quickly move away from the source of the interference. So in that case, that interference would be fairly short-lived. Would the radar altimeter be able to recover from that interference?
So it depends on the model, but we have to know that the transparent time of autopilot and flight control are more about in the order of hundreds of milliseconds, and the radio altimeter refresh rate is 50 milliseconds. So yes, we have to react very quickly upon an erroneous radio altimeter value.
So Terry, I think the bigger picture response on that one is it depends on the type of integration. Some platforms have a additional level of filtering that they utilize. Some platforms utilize the unfiltered radar altimeter output as well. So depending upon platform integration, the impact is going to be varied.
Right, and to add to that a little more, operationally, you know, a very brief interference event may not necessarily be as impactful directly in terms of causing hazardously misleading information or a complete loss of function on the aircraft, but it may become an availability issue. In some avionics systems, an event that brief may cause the pilots to be informed that they cannot perform an autoland. You could also potentially have an erroneous indication from another system like a ground proximity warning system. So the pilots, for instance, could have a whoop whoop pull up annunciation in the cockpit, which is something that they need to take very seriously and respond to. So there's certain system level aspects beyond the radar altimeter that have to be considered there as well.
We're at the end of the hour. I'm going to take on a couple of more questions, but we do have all the questions that have been submitted and who submitted them, and we'll get those to the panelists and attempt to get back to those of you that have asked some questions that haven't been answered here today. But I'll just two more questions. One is regarding the information about the altimeter performance data that wasn't considered. So a lot of critics have said that because individual radar performance data wasn't considered in our analysis, and it should have been, how has that impacted, do you think, the analysis on, and could you describe maybe a little bit about how that testing was done and why having that individual radar performance wasn't necessary?
Yeah, I can speak to that a little bit, Terry. So as I mentioned, the data that was provided from AVSI to RTCA for the purposes of the SC239 study consisted of measured data that had then been combined in the worst case sense across the different usage categories. So the actual underlying test data for individual altimeter models was not shared. And again, from the SC239 perspective, we didn't think that was necessary to have any underlying data because of how we scoped our study. Again, we were trying to identify whether there was going to be any risk of harmful interference to specific aircraft platform types, considering all of the different TSO authorized altimeter models that could be used on those platform types, and not begin to identify specific altimeter models that are more susceptible than others. So I would agree with those critics that identifying models that may be more susceptible is going to be something that needs to be done moving forward, potentially if mitigations are needed. You would certainly want to know if you're an aircraft operator, if the particular altimeter model you're using is going to be affected or not. But that is something we consider to be outside the scope of the SC239 study and better suited to some follow-on activities.
Great. And then just a final question. Has there been any other testing or analysis conducted by either the aviation industry or the telecommunications industry that has shown different results or conclusions from the RTCA or AVSI analysis?
Yeah, Terry, from the perspective of what has been shared in public, we have not seen any additional radar altimeter receive system testing. There's been some additional information that's been shared by filings by other stakeholders, but that has not been backed by a detailed report similar to what we have seen through the auspices of RTCA SC239. So at this time, the only authoritative report that has been vetted in the open is the one that came out of RTCA SC239 in support of this activity and being supported with data input from the AVSI testing activity. Over.
Well, thanks. Again, we've got a lot of questions and we couldn't get to all of them in the time frame that we had, but again, we'll get answers to those questions and get them back out to those of you that have asked so that we can do the best we can to answer everybody's questions. I just want to add on a personal note. I know firsthand the significant importance of radar altimeters in an operating environment. I spent 30 years as an airline pilot, more than 17,000 hours as pilot in command, and I grew my teeth, if you will, in the airline industry with a small regional airline out in Colorado, flying passengers into and out of the ski areas like Aspen and Steamboat, Vail, and some other places, and oftentimes in some pretty nasty weather. In those operations, the radar altimeter was our lifeline. It ensured adequate terrain clearance and avoidance, along with some general situation awareness. Then when I moved to the major airlines, radar altimeters were a key required aid when doing approaches during low visibility Category 2 and Category 3 operations. And as was pointed out in the presentation, they fed some very safety critical data into some of the other airplane systems. But my personal experience aside, I'm certainly aware that this reallocated spectrum issue has a lot at stake. There's a lot of energy, a lot of passion that many stakeholders have, both from aviation and from the telecommunications industry. But our goal was to set some of that emotion and passion aside and produce this report of technical truths by first assessing the potential interference impact on radar altimeters, and then longer term work to update the requirements for performance standards on future radar altimeters against the existing and planned future radio frequency environment. Now, we don't consider this a definitive one-time assessment with this report, but rather we consider it the basis for some ongoing work and analysis. At RTCA, we remain committed to model the operational environment with the best technical data available, and we're certainly open to completing additional testing and analysis, and even revising the results of this report if further inputs become available to us. Furthermore, we're committed to working together with the telecommunications industry in a proactive manner to find solutions that will advance the use of technology, while at the same time ensuring the safety of the traveling public. My thanks again to the panel, Jean-Luc, Seth, and Cy. Thanks to our sponsors, Collins Aerospace, NBAA, American Airlines, and Garmin. And again, this presentation will be available on the RTCA YouTube channel in the next day or so. And to everyone in the audience, thank you for sharing part of your day with us. We appreciate your attendance today. Our next webinar is currently scheduled for Wednesday, January 20th at 1 p.m. Eastern, and details about this webinar are going to be made available in the next couple of weeks. I hope you'll all be able to join us. So thank you and have a great day.